0 or 1 to the variable, true, false to the variable. And then a cost is whether it satisfies what you've been given or not. So for example, if you set x to be 0, then x3 not becomes true, while this one becomes false. And if you have true or something, then this whole clause becomes true because you have a true in the or. And so we have all our, and then the ends, if you have all trues, you get a true, right? So this guy satisfies it, right? And so the problem is you're given something like this, and you want to find a satisfying assignment. So does anybody in this room have any illusion that this is an easy problem? It's not. It's a hard problem. It's the classic NP-complete problem. All right, so we're going to sort of try to build a recursive backtracking algorithm, try to build a dynamic programming algorithm for it and see what goes wrong. And people really do want to solve these things. People like AI people, lots of people want to solve these things. And their method of solving them generally is this recursive backtracking method. When they basically call it Davis-Putnam, but it's basically recursive backtracking. All right, so we have this instance here, and we want to ask the bird a question. All right? So what does the bird know? She knows a solution. She knows the value of every variable. Right? So what's the obvious question we could ask her? Right? What? Value of the last variable. Great. We could, or here I guess I put the first variable. We could ask the value of the first variable, right? And you know, what's wrong with asking the value of the first variable for this example here? It's not very useful, right? It doesn't really help us. You know, branching is bad because it just doubled your time, right? You're doing two things. So you don't want to branch doubling your time unless you have real good reason to do so, right? It's kind of like when you're filling out those Sudoku puzzles, and you know, ideally, every time you write down something, you know that's the right answer. But once in a while, if you have a really hard one, you get to the point where well, I have to guess, you know, do I go for a 3 here or go for a 3 there? And you branch, and you want to do that very infrequently, right? Because if you get the wrong thing, you're going to have to backtrack, and it's scary. All right, so a better thing would be to branch, say, on value of x3 because it appears in more places, right? And so this is, you know, a heuristic trying to do this is going to have some sort of way of deciding what to branch on, right? Maybe it'll branch on the variable that appears the most often, or you know, there are plenty of heuristics. So you ask her the value of x3, and there are two answers she should give. So and again, you have to use a heuristic to see whether you try which to try first, right? So maybe we're going to try. X equals 3, we're going to temporarily commit to that and move forward, and if it works out and we find a satisfying assignment, then that's great, and if it doesn't, we have to back up and try the other value. Right? So if we've committed to x3 equaling 0, what can we do to our input? What, said another way, is what input do we give our friend? Right? What do we need to ask our friend? Right? If we put in a 0 here, what happens to this? This becomes true, so the whole clause becomes true, right? So we can eliminate the whole clause. Well, here, this clause becomes false, so can we eliminate the whole clause? No, we just eliminate that one literal. Right? Does that make sense? So that simplifies our input down to this guy. Right? Now our friend has this, and right, somehow by magic our friend goes and solves this, right? And when our friend comes back and gives us an answer, then what will our answer be? Right? So he didn't give us an answer. You know, x3 wasn't part of his thing because we kind of eliminated x3. So our answer would be the same. We put the x3 equals 0 back in. Does that make sense? It's kind of your classic recursive backtracking. Everybody kind of follow that? Now, it's exponential time, right? Because we branch here on the value of x3, and then maybe our friend branches on the value of x2, and so forth. You get this whole tree. And you know, some things is that just because my left friend branches on x2 doesn't mean my right friend has to. Right? They can have their independent friends. They can do their own thing. But the reason it's exponential time is because if each path branches on all n variables, then, so the depth of this tree is n, that means that the number of leaves is going to be 2 to the n. It's all possible inputs, right? All possible assignments to the circuit. Everybody kind of following this? All right, so now, if we're going to do dynamic programming, we want to say, hey, that was too much. So we want to look at the set of sub-instances. We start with our instance, and we see what are all the sub-instances that ever arise. And what do you think is going to happen here? We're going to have a nice small number of them? No, our wedding party is going to blow up. We're going to just have too many people. All right, so for example, if this was our instance, then we want to say is this a typical subinstance, right? Might this subinstance arise? And it can if you commit to these things, and this arises, right? But in general, you can see that you get an exponential, depending on what you set and how you branch. Everything you get is, every little subinstance is going to be, they're all going to be unique. Every friend, my friends is going to get a completely unique subinstance. So the running time is exponential. Now, the Davis-Putnam algorithm, recursive backtracking, is you try to have heuristics to save you time. Like, so for example, if this was if you were some friend deep in the recursion and you're given this instance, then what should you do? What do you need to satisfy this thing, right? So is there something you know? That this clause has to be true, right? So x3 has to be false, right? So you don't branch. If you see this, you don't branch in this direction, right? You just that eliminates that whole subtree, and that's where why are people actually running Davis-Putnam is because in practice the inputs that arise can be such that you can sometimes solve them anyway. Right? So here's another example. What happens if this was your input? It's unsatisfiable, right? Because this says that x3 has to be 0, and this says x3 has to be 1. So in that, it's kind of like it's a base case. I bottom out and I say, I give up right there, and I tell my boss, hey, no, don't bother with this branch. Right? Does that make sense? So that's the kind of game. And here the Davis-Putnam algorithm is I'm given a set of clauses or a circuit or something, and if somehow it's trivially solvable, then I solve it. Otherwise, I try to branch. I choose some variable to branch on, and I choose which direction to branch, and I recurse.
What's the actual real running time? Given that you can chop off so many things, worst case could be 2 again, but what would it normally run at? If you took a large number of cases.
Well, the hard part there is where are you getting your cases from, right? If you're talking worst case, like I give you an algorithm and you find the worst case input, for every algorithm anybody has ever managed to define, I think the worst case is always, maybe you can get this, I don't know, there's some number here. You can play with that. But then you might ask, well, are the instances that arise in practice, are they worst cases, or maybe life's not so weird? You know, if, for example, I look out at you and I have to see, hey, you're a person and you're a chair, and you know, people have said, you know, vision is incomplete. So how do humans manage to see? Well, you know, the world out there that I see isn't a worst case image. You can be something really weird I'm not going to be able to see. But, you know, I kind of know what to expect, and so my heuristics in my brain tend to work. And sometimes they don't work because, you know, I don't know whether the woman on their internet's spinning left or right. You know, I get confused. Have you ever gotten her to spin the other way? She never. You know, she spins one way.
No, she spins both. Yeah. She does, yeah.
I think it depends. You know, they say it depends on whether you're a right brain or a left brain person or something. But anyway, that's the.
I can see both.
That's the answer to that question. So you know, as I said, people do run this thing, so it works for them. But they run it on inputs of the kind of size that and the kind of quality that works. Because when they don't work, they stop running them. All right. So here's another problem which has been an assignment to this course a number of times. It's a classic problem. I have a chessboard and I have queens, right? And I want to put queens so that they don't kill each other, right? No queen can kill any other queen. So if you have a queen in this column, right, you can have no more queens there, no queens there, no queens there, no queens there, right? And you want to know how many queens am I able to get on the board, right? Clearly you can't put more than 8, right? Because you can have at most 1 per column. And if you were to try it sort of brute force, it would take too long, right? But the truth is, you do some sort of Davis-Putnam, you can do it by hand, and it's really short because things cancel out really, really well. You know, you first say, you know, I ask the bird, where do I put the first one? And you try all the possibilities. But when I'm trying this one, right, it eliminates these possibilities. And so you can, by hand, I've had it in this assignment, and everybody in the class probably copies from each other, but in the end, I get the right answer from everybody, right? So you can kind of brute force it out. Now, you can expand this to say, so now what happens if my board isn't 8 by 8, but it's n by n? You can prove a lower bound that you can kind of show that at least that Davis-Putnam algorithm won't be any better than this. You know, you get a little. You know, this is why it's fast, because 8 over 3 is, you know, small enough that you can do it by hand. But you know, as n grows, this is still a hard problem. Everybody kind of get that? So, what do you need to know when you're doing recursive backtracking? Here's a little review. You can say the first step is I give you a problem, and you say, what are my instances, right? I mean, you really need to know who the characters in the story are, right? I mean, you might think it's not a story, it's math. All right, well then, you know, it's still there are characters out there, right? And in this case, you know, what beasts are the inputs, and what beasts are the solutions, and what are their costs? I mean, when I was marking the greedy algorithms, the problem was that people, you know, as always, people don't know who the various roles are. You know, they'll roll who's the prover versus who's the algorithm versus who's, you know, what people know. What is optimal solution sub loop invariant? Where does it come from? And what's optimal solution sub ours? And where does it come from? And I wish I didn't call it that, because everybody think ours means it's the algorithms, because it's not the algorithms. Because I thought I was the prover, so it's the provers, right? It should be optimal solution sub prover, right? Not sub algorithm. And you need to know who these various people are and these various roles, right? So the first thing, you know, is to keep track of these. And I keep saying it, but you know, it keeps happening. All right, so then I'm given an instance, and I think, okay, my friend has a little bird, right? And I think my bird has an optimal solution, and I ask her a little question about it, right? And what's the typical question you ask? You say, if the solutions is a list of objects, what is the last object in her solution? Or if the input is a list of objects. I ask about the last object. Do we include it? Do we not include it? Do we paint it red, blue, or green? Right? Kind of like you would in a greedy algorithm. Right? So you ask her that question, and in the truth, we don't have a bird, so we have to enumerate over all her answers. Right? And then, now when I trust her, then I know I can fill in some of what I need. And what I need to ask the friend is, what is the rest of the solution? So I have to think, what is a sub-instance I can ask my friend so he will give me the rest of the solution? And when he gives me the rest of the solution, which is an optimal solution, right, he gives me an optimal solution to his instance, which I then construct a solution for my instance by combining the bird's answer with his answer. Right? People getting that? And we do the same for the cost. His cost and the bird's cost. Somehow we can construct the cost of my solution. And why is this good? It's because we get the optimal solution for my input that's of those consistent with his bird answer. Right? And then we do that for each bird answer, and we take the best of those. Right? And that's going to be the best solution to my problem. And then what do I do with it? Right, I'm happy. We wait until, I was going to say we put it in the table, but that's the next slide. Everybody got that? Is anybody unclear about these pieces? I know some of you are, and the way I know it is because I'm going to have to mark it, and I'm going to hate you all in a week today. So ask me now. Right? Think about who these players are and how they interact. Because really, when I'm marking, that's what, if you do anything, you say anything that hints to me that you don't know where optimal solution sub hours, what it is and where it comes from. If you say anything, then I'm going to stone you. Right? What?
Can you repeat what you're not supposed to say?
Said you should stone.
I said it was stone. It's just an example, right? For each little thing, you know, if you go through the steps, each little thing that's in there, like for example, optimal solution sub hours, is something that people get wrong all the time. Optimal solution sub hours. What is this and where does it come from? Right? You need to know that because what I'm doing is spoon feeding you the answers, and I expect you to know what I spoon fed you. Right? So what this is, it's a full solution to the problem, and well, hopefully, actually we don't know that. This is a full solution consistent with what the algorithm has done so far, and the prover changes this into this, and now we have this, and we need to prove something about it. Right? And this needs all the boxes. If this had all the boxes, don't drop boxes, because this is going to be valid, needs all the boxes. Right? So it's a similar thing here. Right? What are the various things you need to know? I have an instance. What is this? What is I? I is you know, it's a set of clauses. Right? What am I looking for? I'm looking for a solution. I'm looking for an assignment to the variables. What's the cost? The cost is, does this assignment to the variable satisfy all the clauses or not? Right? Then I have an instance. I ask the bird a question. What's k? Little k. K is oh, I ask her a question. What's the question? Variable x5, how do I set it? Right? That's the question I ask the bird. What is k? Little k. Little k is one of her answers. Oh, you know, use little k, because then I'll know that we're talking about the same thing, and it makes my marking easier. And man, I don't think I've ever hated marking as much as I did this last time. My mood was, I just was not there. I was not there, I'll tell you. Unenthusiastic. All right? All right, so little k is set it to 0. We're trying to set x, whatever do I set? x7. What do we set it to? Well, you either set it to 0 or you set it to 1. What's capital K? It's the number of answers she might give. Right? And then we loop over them. We try setting it to 0, setting it to 1. All right, if we set x7 to 0, what's the subinstance we give their friend? Well, it narrows down. You know, setting x7 to 0, the clauses get, some of the clauses disappear, some of the littles disappear. This is an instance to the problem that I give my friend, right? So if it's an instance, what is it? It's a bunch of clauses, right? The and of a bunch of clauses. And what does my friend optimally give me? He gives me a solution to his instance, which is in a setting of all the variables that he knows. So in fact, it's a setting of all the variables except for x7, right? And then I need a solution to my problem. What is this? This sub k, right, is his assignment to all the variables except for x7, plus I set x7 to be 0, because that's what the bird told me to do. Right? People following this? You should know what all these pieces are. Right? Because I'm really going to be looking at this. Do you know what that is? Oh yeah, that's the solution that my friend gives me when I give him a subinstance. Right? I need to know, you need to know what all these pieces are in the puzzles. Right? And not only, you need to know what they are generically, but then you need to translate them into the new problem.
Can you explain why the capital K is?
Sorry, which one?
The K.
This K?
The other one.
This K?
Yes.
Oh, good question. This is simply how many bird. This is a bird answer, and this is the set of bird answers, right? So capital K, I usually mean how many bird answers are there, right? And you want that to be small because you're going to have to loop over all of them, right? Good question. Any other questions about this? So then, we have this great recursive backtracking algorithm, but it runs in exponential time, right? So we start with our instance. I'm Mr. Dynamic Programming, and somebody gave me an instance. What's my instance? It's a set of clauses. And I run my recursive backtracking algorithm on it, and I figure out the complete set of subinstances that will ever arise. Right? I have my instance, my friend's instances, their friend's instances, their friend's sub instances, right? And I figure out what this complete set is. And what properties does it need? Well, it needs to contain my instance, and it needs to be closed under the friend operation. Meaning, if you invite somebody, you need to invite their friends, because before you can solve them, you need to solve their friends, right? And what's the problem with this set for the circuit satisfying problem? What's the problem with this set of subinstances? Does everybody? How many people, if I ask you right now, could answer that? Here, let me ask you the question again. Suppose we're trying to solve circuit satisfiability, right? What's the problem with the set of subinstances that arise? How many people could answer that? Does that mean the rest of you can't? All right. All right, so you got to ask more questions. All right, somehow we got to communicate. Right, so I just killed my chalk. Sorry, chalk. All right, so what we're doing here is we're building a table indexed by these subinstances. Right? Those are the subinstances we need to solve. And the running time in this dynamic programming algorithm is going to be the number of instances times the number of bird answers. And the problem here is that there's just going to be too many subinstances. Right? If you invite me, and I invite my two friends, and they invite their two friends, and they invite their two friends, then you have this exponential sized tree. And the only reason you may have a reasonable number of subinstances is those subinstances start sort of colliding and really being the same. You know, my friend's friend's friend might be the same as your friend's friend's friend. Right? So we invite that guy for two reasons. One, because he's my friend's friend, and because he's your friend's friend's friend, right? He gets invited twice, but we don't have to count him twice because he's only one guy. Right? Does that make sense? he doesn't eat twice as much food simply because we know him in different ways. And that's what happens in a nice dynamic, in a good dynamic programming algorithm. In a bad dynamic programming algorithm, everybody's unique, right? And that's what happens when you take an example of a circuit and you simplify it in different ways. Every way that you simplify it, you're going to get a different subcircuit, right? It's going to be sort of a subset of the circuit. If every subinstance is a subset of the instance, then you're going to have too many subinstances. Does that make sense? The only time it's good is when it's a prefix or something, right? So you want to make sure that your number of subinstances is small. So we build the table indexed by these, right? And we fill in the table so nobody waits. And what do we put in there? Well, we would like to put the optimal solution, right? Every square is associated with a subinstance. We have to fill all these. Everybody has to, every subinstance, everybody gets invited, has to be solved. And we would like to put in there the optimal solution, but it takes up too much space. So we put in the cost and the advice from the bird. Right? And after we fill in the table, then we do it again once we have the bird's advice. Right? To give the find the solution. How are people doing here? Are you completely terrified? Yes?
So it says build a table indexed by these subinstances.
Yes.
So the subinstances isn't every space that's in the table, but it's the x and the y.
Yeah.
So it's just x plus y, which is the number of subinstances.
Good question. Let's see. If we were doing shortest path from S to T, what were the subinstances? For each node, V, there was the problem, what's the shortest path from S to V? Right? And because we asked, a friend told us about the last edge. Right? So then the table would be, there would be, if they're in nodes, they would be in squares. And here is node V. And so this problem is the shortest path from S to V. Right? And so then when we fill in the table this way, when we're filling this one, we're saying what's the shortest path from S to V? And we ask our bird which is the last edge. Right? Now if we were doing knapsack, here's our knapsack. Right? The question was, do we put the bear in or not? Right? And then what is a subinstance then? Right? So here this one is, we're going to consider the first I objects, the prefix of the objects, right? Because we eliminated the bear, we eliminated the wagon. We're considering the first I objects, and the knapsack that we have some remaining, we have this much volume left, right? So we're asking our friend, put as many of these objects, first I objects, in a knapsack of this size, and tell me the optimal value that you can put in there.
But I thought that the I and the V would be one subinstance.
It is,
Okay.
because it's one square.
Okay. So how many subinstances? So each square is a subinstance.
Yes.
Okay.
Yes. Right? We need to, for every subinstance, right, we need to have a spot in the table.
Okay. Oh, I got confused because this says indexed by the subinstances.
Yeah, so what's this indexed by? This is indexed by I v prime. Right? This has two indexes, so that's why it's two-dimensional. Right? Does that make sense? This square what we store in this, what it's indexed by, is the subinstance. Right? This is the subinstance which says, consider the first I objects in a knapsack of size v prime.
Okay.
Right? That's what this square is indexed by. And what do we store in there? We store the cost of the optimal solution for it. Does that make sense? Maybe not. We can do it again.
So the subinstance is the square. So the subinstance is the square. Like the, yeah. So what's I and B considered?
All right. So I wouldn't say this is the subinstance. I would say this is a square of the matrix, a square of the table, right? What is this square indexed by? It is indexed by I and V prime,
Okay. So
right?
the number of subinstances is just one. It's just one section.
Each square is a subinstance. Each square is indexed by. Let's finish this. This is a square. What is it indexed by? It's indexed by I and V prime, right? So this is the index. But what do I think about this as? I think about this as a subproblem.
Yeah.
Right? The subproblem is I have the first I objects and I have a knapsack of size V prime. Right? So I think this has a dual meaning. One, it represents my subinstance.
Yeah.
And two, it indexes a square in the table. Right? Has a dual meaning, which makes that confusing. So that dual meaning is what I mean by the table is indexed by subinstances. Why? Because this is a subinstance, because it's of the first I objects in a knapsack of size V. Right? It's a subinstance. But it's also the index into my table. Right? Does that make sense? I mean, basically what we're saying here is build a data structure that will allow you to store for every subinstance the cost of that subinstance's optimal solution. Right? Because we invited you all to this wedding. Right? And we need to solve each of you. Each of you is a subinstance. We need to eventually solve each of you. So each of you is going to be given a table where you can eat, and it's going to give a little box where you can put the cost of your optimal solution. Right? And we could have those boxes spread out in the room, but if we can put all those boxes in a nice neat table, then that's nice. Does that make sense? Does that help people? Any people have any other? I mean, really, seriously. When you're studying for this, this is the way you study. You get the set of steps, which is, I think it's, this is copied right out of it. Right? And you go through the steps. So here you have the set of steps, and then you have all the problems that we looked at. Right? What did we look at? We did shortest path, we did knapsack, we did printing neatly, we did room scheduling, right? For each of those, go through the steps and say, do I see the correlation here, right? Do I know if I'm doing room scheduling, what is an instance, right? What are the questions I ask the verb? What are the subinstances? What's this? How does the subinstances index the table, right? And it's my belief that if you do that, then when you do the test, you'll have some sense of what these words mean, right? You'll have some sense what optimal solution sub-hours means, right? Because you've seen these various examples, and I will read it, and I won't see any signs that you don't know what it means. So I will have no reason to fail you, right? And then, on top of it, you've seen all these various examples, and you'll be able to bullshit about this new example, right? And you really, given the way everybody else in the room bullshits, you don't have to bullshit very deeply before I'm impressed. Right? That's really the truth. Like, for example, the last question of the greedy algorithm, where you had to prove that it gave you the optimal solution, right? The math there was way above your heads, and I debated whether to put that in there or not, right? But it's there, and you know, I really didn't expect anybody to get it, but that's okay, right? Because nobody did.
For these, would you ever give us something that had more than like more than a two-dimensional?
They get harder and harder, right? I mean, the only...
Is it the same idea? You just have more X's?
Well, can you think of an example?
Well, you could have another variable.
Yeah. Did we do an example?
Yeah, we did.
Parsing. Parsing, right? Yeah, parsing. You know, are you going to have to do parsing in 20 minutes on the exam? Yeah, likely not. You know? You know, two-dimensional is nice because I like pictures, and you can get, you know, draw the picture and it helps. Right? I mean, really, I tell you, if in a dynamic programming question, if I see the right picture of the table indexed by something, and this says, hey, this is the sub-instance, consider the first I objects in a knapsack of size V prime, that's in here, and, you know, I just immediately smile, and, you know, sometimes I don't even read the rest of what you write. Seriously, you know? It doesn't take much to make me happy. All right? Any other questions about any of this stuff? These are the same things, right? I just keep saying the same things over and over again, right? Right? Why did I make this slide? Because I spent the day marking. Right?
It was a good day, right?
Oh, they're never good. They're never good. Are people following what I'm saying? Right, so what are we saying here? You know, all these things have the basic code, a basic structure, right? So what I'm going to be asking for, let me tell you what the question is for dynamic programming is. Right, there'll be some problem, which I won't tell you what it is. And then I will probably say, you know, give me the bird French story, right? And you'll say, well, I have the instance is a knapsack with a bunch of objects, and I ask her, do I put the last object into the knapsack? And then I ask them if she will say yes or no, and I will, if she says yes, then I give my friend the same objects minus that last object in the knapsack, which is a little smaller. And if she says, and then I take my friend's answer and I put the bear back in, and that will be my answer. Right? And then she says no, I just eliminate the last object, I take the best of the best. Right? That's what I want in that question. And then maybe I'll have little other questions to warm you up, like, okay, what is the set of sub-instances that rise? Right? And then you say, oh, well, for every prefix of the objects in every volume of the knapsack, we're going to have a sub-instance, and that sub-instance will be of the first I objects. What do I put in a knapsack of size V prime? Right? It warms you up to thinking, okay, what is the set of sub-instances, right? And I want it to be consistent with your last bird thing, right? If you have a sub-instance here, it better have the property that the sub-instances, the instance I give you is included, and the instances that you just gave your friend better be included too. Right? You know what I'm saying? Is everybody following that? And then we might leap right to the code. Right? And what should your code look like? At the top it declares, you know, you're given the input and it declares a table. Well, I better see how that table corresponds to the set of sub-instances you just did. If you told me that I have a sub-instance for every I and a sub-instance for every V prime, and your table is indexed by in, then I'm going to hate you. Right?
I thought you stopped reading after you stopped.
Exactly. Right? Everybody following that? I want the table to match up. And then, what's your code? Well, you block in some base cases, and then you loop over sub-instances. So I'm going to check, am I looping over the sub-instances that you described in the previous thing? Right? Are you looping over them in a reasonable order? And do I know which sub-instance you're now working on? Right? You're now asking, I have the first I objects, and I have a knapsack of size v prime, what do I put in it? That's the sub-instance I'm now working on. Right? Everybody got what I'm talking about? And now within that loop, I'm trying to solve the sub-instance, so I loop over the bird answers. In this case, she says yes or no. It's a pretty little loop. I probably won't actually have a loop. I'll have 2 blocks. Right? And for each block, I look up the answer for my friend from the table. Then I take the best of the best and I put it in the table. Right? Are people seeing how this works? And why do I do this these steps? Is because I don't know. It's my fantasy that I don't know how you could come up with a code without somewhere in your brain having this. Right? You can call it a bird if you want, or you can call it somewhere. But I don't know how to come up with this code. Somewhere you need to be thinking this way. Right? Any questions about it? I recommend that you get together, with friends in here and go over the steps. Say, okay, we're going to do the steps for examples that we've done already in class, right? And examples that are in the assignments and the practice tests, right? And then there are even more in the book, right? And, really, my belief still is that you're all going to do great on the exam. Right? That's my belief. Right? And the reason I have that belief is because, ever since I started having these tests, that's what's happened. All right? So, you're going to look at your test today and you're going to say, oh yeah, maybe he's right. Maybe I didn't really know what optimal solution sub R's is. Right? And that will convince you that yes, that is what you need to learn. Right? All right, so this says, yes, the codes are all the same, but don't give me code for longest common subsequence. Right? I don't want the code for longest subsequence. I've seen it before. And I never know what mark to give you for that. 5 minutes, all right. Right? And, right? Then don't use the words from other problems, right? Don't say this if our problem doesn't have a variable c. And you laugh, but I just finished a horrible week marking, and that happens over and over again. People say, I know this doesn't, it's consistent with the previous things because it doesn't have any conflicts in it. What does that mean? Doesn't have any conflicts, right? I mean, at least put it up in the valid case, because that's where I use the word doesn't have conflicts. It's valid, right? But I need to know what that means, and yeah. Right? So this is things I've said. When looping over the sub-instances, be clear which one's being solved. Right? If the sub-instances are prefix, then you only need, it's indexed by I, so your table is indexed by I, that kind of stuff. Be clear. Let us know what the bird answers are. You can find these on the slides. Go over and think about them. All right. So what's happening from now on? We have some number of classes left, depending on who you believe, and 4. So Friday's not a class because it stops on Thursday, eh? All right, I think I have my notes, I said Friday's a class, but maybe Friday's not a class. I'm willing to stop. So make sure, I will keep teaching new material, like I will teach you MP completeness, and then I'll teach you the halting problem, and then I'll teach you something else, unless you come up with questions. Right? I also do have a set of slides, which are, basically it gives you the steps for every section, and we kind of review them. But yeah, start studying now. Any other questions? We go home. Have a great Monday night.